Welcome to, or welcome back to, our advanced series on radio design, in particular radio receivers. Today, we're going to be talking about low noise amplifiers, noise analysis, and ultimately how to find noise figure. In particular, how to find noise figure of a circuit, such as this tuned RF amplifier over here on the left. If you've seen some of the previous videos in this Radio Design 401 series, then you'll probably recognize this diagram right here. This is hinting at what noise figure is, and we're going to go deep into it today. But basically, we know that the antenna is receiving some signals and it's trying to contend with some interferers and possibly radio frequency interference that we've discussed in previous episodes. But there is background noise coming into the antenna, and it's given by this formula that many of you may know. The noise power is Boltzmann's constant times temperature in degrees Kelvin times the bandwidth in hertz. Now, that is competing with our signal. But once it gets into the receiver electronics, there is extra noise introduced by the electronics themselves. And that's kind of our topic today. We're going to discuss how that's quantified and how that leads to particular noise figures. However, we're going to go way beyond that. That's what a lot of other videos that I've looked at on YouTube do, but we're going to look at this from a systems perspective. So I've got a couple examples here from the real world. This slide looks at marine GPS antennas, but not really the antenna so much as the low noise amp and some of the things that are done in the design of these. So a GPS antenna is, of course, trying to give us our coordinates when we're out on the sea, the ocean, whatever. And here's one. It's mounted on some stanchion on what looks like a motorboat. There's some sailboat masts in the background here. But there's also things like this. I think this is the VHF communications antenna. And I'm not sure what some of these other ones are. This is a nice blog page that you could go to if you want. But I was mainly interested in this photo because it motivates what we're going to be talking about. So in our little diagram down here, we have our antenna. That's this, of course. And then we have all this stuff coming in, from different directions and from different signals at different frequencies. In particular, we've got interferers, and they're blatant. I mean, if you're transmitting on the VHF radio, then you're just pounding this thing. And you've got to protect the low noise amplifier from that very strong signal. And that may be true of these too. I'm not sure what these are doing. But I really want to call your attention to the fact that most of these signals that are, actually all of these signals that are competing with this GPS are what we call out of band. GPS is at 1.5 something gigahertz. This is at 160-ish megahertz, etc. And so you could filter things out. And that's what we do. So here's the antenna, right? But what the antenna really is this dielectrically loaded patch antenna inside the white housing, which is a radome to keep the water off and so forth. And that antenna then, on the back side, there is a preamp board. And we're going to go back to this in a second. But I want to point your attention to the fact that there is this cable coming out, and this cable is typically 10 meters long. And that gets you into the cockpit of the boat. Now, we're not so much interested in the boat itself as we are in a low noise amplifier. So let's take a look at the electronics that's on the back side of this. So this is a metal plate, basically a ground plane, and on the back side is what we see here. The signal from the antenna comes from the other side on this pin right here. And the first thing that it goes through is a filter. This is a very narrow bandpass filter. And that's to block all of those interferers. And then it goes through a DC blocking cap because it's going into Q1, which is not really just a transistor. It's a monolithic microwave integrated circuit kind of thing that requires power. That actually comes up through the coax. And then there's a DC block, so it doesn't go anywhere there. It goes up here through the squiggly line, which is some inductance. There's more inductance here, and then there's capacitors. So that is filtering out RF, preventing RF from taking this path. But the DC goes up here, goes through here, goes over here, goes over here, goes down here, and then goes to this pin on the amp, which powers the amp. Meanwhile, these flanking things here are grounds, and of course this is the input, AC coupled. So pretty neat electronics in here, but the important thing is this filter. This is an older style dielectric resonator 2-pole filter, but I pulled a data sheet for a newer GPS filter that you'd probably find in one of these things today. This is from Corvo, and it's a surface acoustic wave filter, and they've gotten these things working really good. It has less than 2 dB of insertion loss. But let's take a look at the frequency response. So the GPS band is right here, and then it just has super sharp skirts, and on the low frequency side looks like the rejection is about 40 dB minimum, but down in the 160 megahertz range it's 50 or more. And it's really good at getting rid of cell phone signals, which are kind of in this range, I think. Not sure, 2.4 gig, right? It'll get rid of that if there's any kind of Wi-Fi antenna anywhere near, and so forth. So in a systems context, that's what we need to do. We need to block the out-of-band interferes. The band in this case is just the width of the GPS signal. But we need to block all of those interferes so they don't overload the poor little low noise amplifier. And lastly, before we leave this slide, I want to make a note that this coax that goes back to the cabin of the boat, 10 meter long, has a lot of loss in it. And that, of course, is the reason that we mount the LNA right at the antenna. Now, our second real-world systems example are receivers in motor vehicles, an automobile. And a modern automobile has usually some kind of a little antenna that looks like maybe a shark fin. You can see it here in the back on the roof. But the actual antennas depend on what you're doing with. The GPS antenna is over here on the right. And the FM radio antenna is actually a wire that extends across the back of the roof, not under the metal, of course, but near that, and then down the pillars. And we saw that in a previous video, a diagram. Now, let's take the FM broadcast band as an example. Again, the car has many other bands and signals coming in, but let's just take the FM broadcast band, because that's been our focus or example in this video series so far. The FM broadcast band is pretty wide, and there tend to be dozens of signals in it that we might want to receive. And what people do in receiver design is they generally pass all of those signals on to the low noise amplifier. And we'll see reasons for that as we go. But the signals then I'm calling in-band interferers. They're in-band because if we look at the block diagram over here on the right, there is a so-called pre-select filter that blocks things like Wi-Fi and frequencies that are well outside the FM broadcast band. But the entire band goes through this filter. And then it hits the low noise amplifier. And if there are some really strong signals, more than one, for example, they can mix together and create what are called intermods. And for details on that, see episode 4 in this Radio Design 401 series. But the main thing I want to point out is, unlike the GPS case, where we could filter down to a single signal because it was at a fixed frequency, here we have to contend with interferers that could be at any frequency all across the band. And that's been our problem. We're going to figure out how to fix that. So we really have two different cases represented by those two examples. In one case, we definitely need the low noise amplifier. It needs to have a low noise figure because satellite signals like GPS are extraordinarily weak. So we have to get close to the theoretical noise floor of the stuff coming into the antenna. And so high gain to overcome the loss of the 10 meter coax cable and low noise figure are sought after in that case. But in crowded spectrums, like the FM broadcast band, for example, but it could also be Wi-Fi bands and all the other things that these days are being crowded with multiple signals. In crowded spectrums, when you have decent antennas, the amplifiers will produce intermods. And it turns out that the low noise amplifier noise figure may not be as important as that. If these intermods are much stronger than the noise floor, like minus 70 dBm versus minus 120 dBm for the noise floor, then, what good is a 3 dB noise figure? But again, if you're trying to receive satellites, you definitely need low noise figure. So our problem has generally been intermods themselves. And down here at the bottom is a picture of this that I hope illustrates my point. This is a Tiny SA Ultra spectrum analyzer, a really cool instrument that you can get for about a US $150 or something. And it'll show you the FM broadcast band. But if you turn on the low noise amplifier and you have a decent antenna, something that's not tiny for an antenna, then it's going to generate intermods. And these are all intermods. This is above the top end of the FM broadcast band. There are no signals in the environment here in my location. And likewise down here at the lower end, below 88 megahertz. And some of this stuff here is also intermods. We turned on the low noise amp because we wanted to see signals down to a minus 120 dBm. This is minus 100, minus 110, minus 120. So we wanted to see signals down to the noise floor, but we can't because they're all covered up with intermods. Bummer. So what can we do? Well, the answer to that involves going back in time. Down here at the bottom is a hi-fi receiver that I got when I was in high school and college. And it's got a really good FM radio in it, better than ones you can buy today, in fact, in many ways. What's better about it? Well, it can receive signals that are very weak down to near the noise floor, where having a low noise amplifier with a good noise figure matters. And how does it do that? Well, this is the architecture. Many of you recognize this as a classic super heterodyne receiver, but this particular one has what's called tracking preselect filter, also a tracking image filter, but it's this preselect filter that I care most about. Remember, this preselect filter is protecting the low noise amplifiers from strong signals. But this filter is as narrow as possible. In this particular receiver, it's probably a couple of megahertz wide. Now, how does that work? Well, you have to tune it when you change the frequency of the receiver. And that's done with some ganged capacitors that we can see here in the back. And then I have a blow up of it here. So this is where the antenna comes in. There's a balun here for the 300 ohm case, and then it's converted to 75 ohms. It comes in on this little coax. It goes into the low noise amplifier cavity. I've got these shielded cavities here before it hits the mixer, which is over here. But there are inductors in this cavity, and they resonate with variable capacitors. And it looks like there's, let's see, 1, 2, 3, 4, 5. Well, okay, so these big ones are for the AM broadcast band, but these smaller ones here, here, and here are for the FM band. One for each filter and one for the local oscillator that's used in tuning. And they vary together, of course. So this old single conversion super heterodyne architecture is actually better than most of the radios today because it's able to protect the low noise amp and mitigate the intermod problem and allow us to get to signals that are closer to the noise floor. So to summarize all of that, the low noise amplifier is there to increase the signal level so that downstream components like this mixer and everything else that generally introduce lots more noise don't contribute much in comparison to an amplified signal. So the LNA is needed, and this one has a pretty good low noise amplifier in it with a low noise figure. But it has the tracking preselect filter that protects the LNA from strong, not out of band, but off channel signals. As long as your interferer is a few megahertz away, then it's going to get attenuated in this architecture. But the filters must be narrow, and they must track with the LO tuning. And it turns out that that's kind of hard to do in an integrated circuit chip. And I found that out when I was investigating this problem long ago and working on my PhD. So if you're interested in some of the details of that, here is a reference to that dissertation. But moving ahead 30 years, this is what we've ended up with. There are problems with putting the filters on the chip, discussed in that dissertation. It's very difficult to do, almost impossible to do economically, if at all. So narrowband filters are difficult to do on chip, so I'm going to do what's called punt. So that's a reference to a football term, right? You just give up and try again later. So how did they punt? Well, they're going to rely on attenuators to deal with strong interferers. So if you look at this architecture, this is from a patent from one particular company, but it seems like most of the radios these days do this or something like it. And there's an RF attenuator right after the antenna. That's a really, really bad idea when you're trying to get low-level signals. But it's needed to attenuate the high-level signals. So yeah, you can get rid of the intermods, but in the process, you just wreck the noise figure of the low noise amplifier. So these two guys together could have really bad noise figure. So to summarize those points, the system implications, the low noise amplifier design implications here, are that these modern fully integrated receivers make extensive use of automatic gain control and RF attenuators that wreck the noise figure. Plus, they tend to burn more power because that'll help reduce the intermod problem. And you can do that in a car. For example, I recently bought the radio that is used in my car here, and I'm going to do a teardown video in the future to show you kind of what's inside it. But they can burn, up to an amp or something, and you can't really do that in low power applications, portable stuff that runs on small batteries. So this solution is not really suitable for low power applications, and the system noise figure, because of that attenuator, can be up to 30 dB. Wow. So what do we do? Well, in Radio Design 401, the previous episodes, we've been talking about that. In particular, episode 1 introduced our solution, or it's a partial solution. And this is kind of researchy. This is not being done as far as I'm aware. But we've shown in episode 1 that it's feasible. And so we're pursuing it. Now, I want to pause here for a second because I want people to consider that this is not the solution. This is a problem that we've been talking about in this series that needs a solution. This is one possible solution, but there are others, maybe, and I'm hoping that people will be inspired to look for those other solutions. Now, in our case, we're going to be continuing on this for the rest of this series. Again, see episode 1 if you want to understand what I'm showing here. Basically, it's a low noise amp that has a tuned output and then some feedback. And it turns out that creates a sort of pre-select filter, which is very, very narrow band. We can start out with a 3 megahertz filter here in the tuned RF amp and collapse that down to 200 kilohertz. Why 200 kilohertz? That's the channel bandwidth for FM broadcast. So we want to get down to the bandwidth of a single signal. And then it'll be a bandpass filter and block all of the other signals. Now, this video is about noise and noise figure, but what we need to do now is analyze this and make sure it's not going to have a terrible noise figure itself. So we need to understand the noise figure of this. And that's where we're going. So here's our outline for the remainder of this video. This is actually part 1, and we're going to get through the first 3 bullets here. We're going to look at noise figure definition and the basics of that. And we're going to do the math, and we're going to talk about what noise figure really is. Then we're going to look at how do the circuit components introduce noise that results in an imperfect noise figure. So we're going to look at circuit level noise models. And then with those models, we'll talk about analyzing the circuit, reasoning through it, understanding where that noise comes from, but most importantly, which components are the ones that are causing the biggest problems so that we can kind of optimize that and lower it as much as possible. And then in part 2, we'll pick up on that again and then talk about how to simulate it, because doing the analysis is kind of a pain, but you have to do it in order to understand the design that you're shooting for. But once you've got that, we need to simulate, and we'll do that with some examples. And then finally, we'll talk about measuring noise figure. All right, so that's where we're going. Here we go. So what is noise figure? Well, let's look at this little box down here at the bottom and the final note. It says noise figure is the amount by which the ideal sensitivity is degraded by circuit noise. In this case, I'm talking about the ideal sensitivity of, for example, an entire receiver. And so in episode 2, we actually derived this equation. It says that the minimum signal that you can receive well is equal to minus 174 dBm plus 10 log of the bandwidth of the signal, plus the signal to noise minimum that you need to receive it well, and that depends on the modulation type, typically maybe 10, 15 dB. But it also says plus noise figure of the overall receiver. So the ideal sensitivity is all of this without the noise figure, and then the noise figure degrades it. And the pluses are the case when this is all in dB units. Notice minus 174 dBm. Minus 174 dBm is the noise power when B in this equation up here is 1 hertz. And when T is the so-called standard temperature of 290 Kelvin. This equation will change, for example, if you've got a satellite dish looking up into the sky. But for most terrestrial work, the magic number is minus 174. So this is what I'm calling an implicit definition of noise figure. It's not the traditional one. I'll show you that on the next slide. All right, so here is the traditional definition and a lot of nitty-gritty. And so this slide's going to take a little bit of time, but let's work through it. First of all, there are a couple of different things. One is called noise factor and one is called noise figure. They're both qualitatively the same thing, but noise figure is traditionally done in dB and noise factor is just not in dB. And here are the equations. We start with noise factor, and it's defined as the input signal to noise ratio, that's at the antenna, divided by the output signal to noise ratio, which for a receiver system is the D-mod input. But you can apply this to anything. So you could apply it to a single amplifier, just a low noise amplifier itself, or to the front end of the receiver, which is the most critical, or to the whole receiver. Now, if you take this expression, signal input divided by noise at the input, divided by signal at the output divided by noise at the output, and you rearrange it algebraically, you can get this expression where G is the power gain, the signal out over signal in. And I'll let you do the algebra to prove that to yourself. I put this arrow here because this is a very, very useful thing to understand and remember. It says quite simply that the noise figure, noise factor here, that the noise factor is the total output noise divided by gain times input. Oh, that would be the output noise if the amplifier didn't add any noise itself. But the amplifier and other things surrounding it will add noise. And so we're going to work through this little figure here and try to understand that. So this elaborates what the other block diagram was showing, but we've actually got some circuit components shown. We also have the desired input signal with its power coming in and the background noise with its power coming in. And in the first graph down here, we're showing kind of a little spectrum analyzer trace or something where the background noise is 1 femtowatt. Now that's within the information bandwidth of the signal, but I'm just drawing a line here and labeling it 1. So think of this as kind of a little spectrum analyzer with a resolution bandwidth set to the signal bandwidth. And then the signal is this little guy popping up here. In reality, there'd be modulation. It would be spread out, but I'm just showing it as a CW continuous wave signal strength of 4 femtowatts. So what's the signal to noise ratio? Well, it's 4 divided by 1, which is 4, which in dB, because this is power domain, would be 6 decibels. Now let's just walk from left to right, from the antenna, where we start with a signal to noise ratio, which is probably useful. We could probably receive this signal. It may not be great in fidelity, but we'd be able to hear the signal. First thing we go through is a transmission line. And in this case, it's a pretty short one. I labeled it -1 dB. So the loss in this transmission line is only 1 dB, so it's pretty good. And if you take that out of dB and put it into power gain units, it's 0.79. And then the next thing we go through, like in our first example where we did a GPS receiver antenna, we had a pre-select filter out in front of the LNA. And in this case, I labeled it -2 dB. That's typical for an older GPS antenna. New ones might be maybe -1.5 dB, but yeah, it's in the ballpark. And here are the so-called linear power units for that. Now, the LNA is over here, and it boosts the signal by a gain of 10, or that translates directly to 10 dB, coincidentally. And I've labeled it as having a noise figure of 0.8 dB. So this is a really, really good LNA. But having that really low noise figure is not really going to help here because of all the loss in front of the LNA. So let's walk through and see what happens. We start out on the left with signal to noise ratio of 4 or 6 dB. And then we go through, I'm just going to take both of these as a unit. So 0.79 times 0.63 is 0.5. So it's a power gain of a half, and that's -3 dB. Oh, yeah, we could have done it this way, right? -1 plus -2 is -3 dB. So we're losing 3 dB through this thing. But I like the half number because I want to work in the linear units over here. So our signal power was 4, but it got cut in half, so it's now 2. And what about the noise power? Well, the 1 femtowatt got cut in half, but there's losses, resistive losses involved here, and that's where the loss of the filter and the transmission line come from. And so the way this works out, it's hard to show, but really easy to work with. If you stand on the right side of this filter and you look back through, you just see a bunch of passive losses and then the signal coming in. Now, if you stand here and you look back, you end up using the same equation, KTB, at this point, looking backward. And so even though the 1 femtowatt got smashed to half a femtowatt, the extra resistive losses added noise, and the net result is we still have 1 femtowatt. Got that? Okay. So the signal to noise ratio, which was 4 coming into the antenna, is now 2 because of these losses. And that's 3 dB, and that's probably not enough to demodulate. So we've already been hurt by these guys. Now let's look at the LNA. We bought a really good LNA. It has got a 0.8 dB noise figure, but it's not going to help us. Let's see why. Well, we got 1 femtowatt of noise. We amplify it by 10. We get 10 femtowatts of noise. But the LNA itself adds about 2 femtowatts of noise from its circuits components, which we're going to talk about coming up. And so the net noise is now 12. The net signal power is 2 times a gain of 10, which is 20. And so our signal to noise ratio is 20 over 12, which is 1.67. And if we map that to dB by using 10 log of this number, we get 2.2 dB. So we went from 6 dB down to 2.2 dB, even though our noise figure on our LNA is only 0.8 dB. So in that discussion, I was implicitly using this equation here, where I was just mapping from noise factor that we were working with to noise figure by doing 10 log of the noise factor. All right, but let's look at the notes down here. Signal to noise ratios we were working with are in, sometimes we call them linear power units. It sounds like a misnomer, not in dB, so these graphs. The signal to noise values and gains are shown as power ratios up here. and their dB equivalents. We already worked it out, but let's look at it based on this formula, because remember, this is the one I want you to remember. This is the one that's very useful. So if we just compute it directly, the noise factor is what's in parentheses here. It's the total gain, which is 0.79 times 0.63 times 10, that's here, times the 1 femtowatt that was coming in, and that's the ideal output noise. And the actual output noise, because the LNA added 2 femtowatts, is 12. So the noise factor is the total noise output divided by the ideal noise at the output. And that's what this is. And then we take 10 log of that, and we get 3.8 dB. And remember our implicit definition? The noise figure is the amount by which our sensitivity, or in this case, the signal-to-noise ratio, is degraded by going through the noisy stuff. And here, it works out to be 3.8 dB, which coincidentally is 6 dB minus 2.2 dB. So this all ties together. Or directly in terms of dB, we have signal-to-noise ratio at the input here, minus signal-to-noise ratio at the output here, and that's 6 dB here, minus the 2.2 dB at the output, and it's the same number, of course. Even though the noise figure of this wonderful LNA that we bought is only 0.8 dB. What messed up our sensitivity are the losses out in front of the LNA. And that's why these GPS antennas, if there's a long coax after them, have to have an LNA mounted right at the antenna, on the backside of the antenna in this case. And they have to have enough gain to get over the losses in the cable, plus then some, because we want to get over the noise added from the mixers and other things coming later. And this really is the block diagram I was just showing you. We come from the antenna, through a filter, and then through the LNA. Now there's no explicit transmission line loss here, although, you know, this line maybe and this line, maybe that's 1 dB, whatever. We need to minimize the losses ahead of the LNA. In this case, in the case of the GPS antenna, it was kind of unavoidable because we had to have that pre-select filter to protect the LNA against the strong signals. And there's always a little bit of transmission line loss too, perhaps. Now, our LNA 0.8 dB did help us a little bit because it means that we didn't degrade ourselves even further from this 3 dB. We only added another 0.8 dB from using this LNA. So a good LNA is still valuable, of course. So how do we design a good LNA? Well, we have to understand the noise that the circuit components generate, and that's what we're going to talk about next. All right, let's dive deep into circuits. How do we find the noise figure of an LNA given, for example, the schematic diagram? Well, here's an example. This is a simple common base tuned RF amplifier that I'm calling an LNA. We'll see how low the low is. And this is from our Radio Design 101 series. If you're rusty on RF circuit design, I would recommend that you go look at that Radio Design 101 series. It's actually adapted from a university course, and it goes through all of these things here. But I'll assume that you've already done that, or you're working in the field, you're very familiar with this kind of stuff, and let's just plow ahead. We have several parts here. The antenna we could model as a Thevenin equivalent circuit, which is usually the way it's modeled. So the power from the signal that we've been talking about, we could map into a voltage if we know the Thevenin source resistance, which is typically, say, 50 ohms. Then this part up here surrounding Q1, this is a common base amplifier. The base is AC grounded through C4. Signal comes in on the emitter and goes out on the collector. Okay. But it's a tuned RF amplifier because there is L2, C2. So this is a bandpass filtering operation. And as you look into this amplifier, it has perhaps a different impedance than 50 ohms, and so we know that impedance matching might be helpful to get as much of the signal power as possible into the thing. That'll probably help our noise figure. And so we have a matching network. And likewise at the output, depending on what you're driving into, let's just assume we got 50 ohms here, we can match down from whatever the impedance level is at the collector down to 50 ohms. So we got two matching networks. And the question is, how much noise is introduced by all these circuit components? Well, let's find out. So let's start at the antenna. In our original block diagram, we talked about the power coming in of the signal and the power coming in of the noise. But now we're in the circuit domain and we translate that to voltage. And there is noise voltage here. And it's in series with the signal voltage, so it adds to it. Now, important point, V sub n, the noise voltage, is a random waveform. It's not correlated at all, or it's not sinusoidal like the signal waveform. But we'll get to that in a minute. So here is the model for the antenna. How much is the noise voltage? Well, here's the expression for it. It's the square root of 4 kT R sub s times B, the bandwidth. Now, I'm not going to really derive this, but I'll give you a hint as where it comes from. The power is kTB, and we know that power and voltage are related through resistance, V squared over R for power, and you put that together. Oh, where's the 4 come from? That comes from the fact that this is an open circuit voltage, whereas this power coming in is assumed to be going into a matched load. All right, let's look at some actual values. Let's take an example, 290 Kelvin for the temperature. We'll assume 200 kilohertz for the bandwidth, because that's FM broadcast, just been our example going through this. Doesn't have to be that, could be anything. RS 50 ohms for our antenna. The noise power then is 0.8 femtowatts from this expression. Or if you like dBm, minus 121 dBm. This is the power to a matched load. How much is the corresponding noise voltage? Well, we just plug into this formula right here and we get 0.4 microvolts, RMS. And this is the open circuit value. So that's a little confusing, but you really have to keep track of whether or not you're talking about loaded stuff versus open circuit. This is circuit analysis, so we have to be careful. I'm using open circuit voltage because this is our model. That when we do that circuit analysis, we're just going to plug this in and use this as our value here. Okay, moving on, along the way we have, say, R3 next. So let's take a look at it. R3 is a resistor. Its noise model is traditionally given this way, a resistor in series with a voltage source, although it could be a Thevenin kind of equivalent where you've got a resistance in parallel with a current noise source. The voltage noise source is the same as what we just used for formula. The current noise source is shown here. And either one can be used in our circuit analysis, of course. They're equivalents. Now, I skipped over the input matching network. I just went to the resistor, but let's go back to the matching network. We've got an inductor and a capacitor, so how much noise do they introduce? Well, if these components are ideal, meaning they don't have a lot of series losses or something like that, then it turns out they don't introduce any noise at all because they are reactive elements, energy storage elements, not energy dissipating elements. So to a first order, the capacitor is just a capacitor and the inductor is just an inductor when we do our analysis. This is approximately true if the quality factor of these things is large. If Q is not large, what could we do? Well, we could put a series resistor here to model the so-called ESR, equivalent series resistance to the capacitor, and then we could use this as our noise model to make a more elaborate noise model of this. But I like to assume that Q is large on first analysis, and that just makes life a lot easier. And oftentimes it's true. Now, the next thing in line is Q1, our transistor. It's a bipolar junction transistor. And here is a simplified but useful noise model for that BJT. The principal noise is generated when the electrons leave the emitter and go into the collector. And that noise is a so-called shot noise. You can Google that if you want, but here's the formula for it. And the noise model includes a noise source that's connected between the emitter and the collector as shown here. I-noise collector is what I labeled it. So I-noise collector is 2QIC, that's the bias current in the transistor, times the bandwidth. What's Q? That's the electronic charge, 1.602 times 10 to the minus 19th coulombs. Anyway, take the square root of that, and that's our value for the RMS noise current that is, say, going in and out of the collector. When I'm doing noise analysis with this model, with BJTs, I often switch to this formula, and I'll let you try to map between here and here based on expression for GM in terms of IC and so forth. But this is a useful expression as well. Now, there is a little bit of base noise too, because there's shot noise current going out the base, and so you can put that in. I find that that doesn't usually dominate. It's usually this collector noise, but you can put it in. And then there are other things like series resistance in the base lead and the emitter lead in the semiconductor that are going to probably be even less noise. And you could get a really complicated model here, but we're not going to do that. I like to keep things simplified. So that's it for the components that are here. And so with these noise models, we can now try to, or at least estimate, the total amount of noise at the output versus the amplified input noise. And that'll give us our noise factor and ultimately noise figure. So we want to analyze the circuit using circuit analysis techniques with one twist that we're about to show. And then after we do that, we might have made some simplifications, so maybe simulate it, because the simulator can take into account all those nuances, and it can also check our work. And then finally, the proof is in the pudding, so you build a thing and you measure it. So this is where we're going. And we'll do that in part 2. However, don't go away, because I want to show you one other thing, very important. When you're doing the circuit analysis, we're going to talk about in part 2 that when we add the noise voltages from all the different components to find out the total noise voltage at the output, you don't just add the numbers that we just talked about. You do an RMS calculation instead. So we'll talk more about this in part 2. And we'll look at the total output noise, that's this one here from this amplifier. And the amplified input noise, that's this blue curve here. And then we can use the formulas that we learned today to calculate the noise figure. And this is from a simulation, of course. So please join us for part 2 coming up, hopefully in a few days. All right, bye.